figured it out. Okay, so hello everyone. Sorry for the technical difficulties that we're facing at a distance. Thanks for staying for my talk. This is the decidability and complexity of interleaved bidirected Dyck reachability. This is a joint work with Adam, Husted, Kjelstrom, and myself, both from Aarhus University in Denmark. So this is clearly a session about CFL and Dyck reachability. So I'll quickly go over the problem itself. So this is a very standard formalism in static program analysis. The problem is basically phrased with respect to an alphabet of different parenthesis symbols. So here we have K of those, opening and closing parentheses, indicated by these subscripts with integers. And then we have the language of properly balanced parenthesis strings, which is a context-free language, also known as a Dyck language. Right? And at the same time, we have a graph like the one on the right. This is a directed graph together with an edge labeling function that assigns different parenthesis types of opening and closing parentheses to the edges of the graph. Right, and the task is now to find paths in this graph that connect different nodes. But as opposed to standard reachability, where any path is as good as any other, here we focus on Dyck reachability, which means that the witness path should be one that produces a string of properly balanced parentheses. So for example, here we can go from X to Z by means of this blue path because it produces this nice balanced string. And so we say that Z is reachable from X, whereas, for example, W is not Dyck reachable from X, even though it is reachable in the standard graph sense. So this is a Dyck reachability problem. Here's a Dyck graph, find which nodes are reachable from each other. And this has truly numerous applications in static analysis. I mentioned here a few like alias and data dependence analysis. It also has applications somewhat beyond static analysis, like in databases or network analysis and protocol security, and many, many others. And a shout out to a nice tutorial we had on Monday by Kuhn and Tom on this problem and different variants of it, different applications of it, and so on. So that was a nice tutorial that I invite you to watch over on YouTube if you haven't done already. Which also makes my life as a presenter somewhat easier now. So, okay, so the talk is about interleaved Dyck reachability. This is an enhanced form of Dyck reachability. Generally, the graph here serves as a program model, and the labels here are used as some kind of sensitivity in our static analysis so that we increase its precision. For example, it could be context sensitivity. So in the interleaved Dyck reachability, well, we are spicing up the formalism a bit so that we retain a bigger sensitivity analysis. So for example, let's say that we have a program like the one here on the left, and we want to perform some sort of data dependence analysis. So essentially what we do is that we follow def use change in the program, right? So the graph model of this program would look something like this. For example, we have an edge from A to V to denote the fact that this integer A down here is passed as a parameter, as the second parameter in the set X function, so it flows into V. Right, so this is captured by a single edge here, and now indirect data dependencies in the graph are captured by well, transitive reachability relationships. Sorry, data dependencies in the program are captured by transitive reachability relationships in the graph on the right. Now, for reasons of increased precision and for reasons of context sensitivity, we might convert this graph into a Dyck graph. We do so by introducing different parenthesis symbols. Here, instead of parentheses, we will have these curly brackets. And we do so, for example, whenever we have a flow edge that corresponds to a call to a function or a return from a function. For example, here we have this open parenthesis of type 10 to denote that, in fact, the flow from A to V occurs in a call site that takes place in line 10 in the program. And similarly, we close this parenthesis of type 10 to denote that, well, P that has been modified up here flows into Q at the call site 10. Right, so instead of a standard reachability, here we look into Dyck reachability, in order to respect context sensitivity, so our analysis becomes more precise. Now, besides calling context, we might also want to respect field accesses whenever we have, object-oriented languages with composite objects. In particular, we would like to distinguish between the different members of P that we access, right? So here we access P.x. In some other place, we might be accessing P.y. So to distinguish between these, we have edges that are now labeled with parentheses that correspond to field accesses. So for example, we have this edge from V to P to denote that, well, V doesn't flow into any member of P, but it actually flows into the X member of P. And similarly down here, we're not reading from any member of R, but in particular from the X member of R, which is captured, by closing this X-type parenthesis. So now our problem has become more difficult. Instead of plain or even Dyck reachability, we're talking about interleaved Dyck reachability with respect to two languages. One Dyck language captures calling context, the other captures field accesses. And the witness is one where that produces two different Dyck strings, and each of them has to belong to the corresponding language, right? For example, this path here, well, if you project on the curly braces language, on the context sensitivity part, you have a Dyck string there. If you project on the field accesses, you have another Dyck string. So any arbitrary interleaving of the two will belong to the so-called interleaving of the two languages. So this is the problem of interleaved Dyck reachability. Now, this has tremendous applications in static analysis. It has a very large modeling power, and it's very appealing. In some sense, its modeling power is too large because we know that the problem of deciding decay reachability, so interleaved Dyck reachability, is an undecidable problem. We've known this for a while. In a sense, this corresponds to taking the intersection of two context-free grammars and checking for emptiness, which is also an undecidable problem. But nevertheless, it has seen numerous applications. People rely a lot on approximations or anytime algorithms to handle this, or cigar loops, just because it's so convenient to model program analysis using this problem. Now, another technical term that appears in the title is that of bidirectedness. And well, thankfully, the previous talk also discussed this. So just to briefly reiterate, bidirected graphs are graphs where basically opposite edges have opposite parenthesis symbols. So you open a parenthesis of type I as you go from X to Y, if and only if you close it as you go on your way back. Right, and this bidirectedness arises in some subclasses of static analysis. It's used to handle mutable heap data, and it's frequently used to model data demand-driven alias analysis. And it's also kind of a standard in the CFL formulation of pointer analysis. And here are a few papers. Then just to give you a flavor of where this bidirectedness might arise, at least the way I understand it, well, Dyck reachability formulations of inclusion-based alias analysis basically decide whether pointers may alias by looking at the heap objects that they may point to at runtime. And so a program like the one on the left would have a flow graph like the one on the right, where again we use some kind of parenthesis here to model field accesses of composite objects. And the inclusion principle basically tells you that if you have two aliases, then well, they may point to the same points to sets. So you would actually like to have a way to have this object O2 here flow on Z here, because Z and Y are aliases. And unfortunately, in this Dyck formulation, you cannot infer such a path. The trick is to add these inverse edges, and this now allows you to conclude about these relationships that you would like to have there. So this is just a very, very brief sketch of where bidirectedness might arise. So we have arrived at the topic of this paper, which is if you combine interleaving and bidirectedness, you get interleaved bidirected Dyck reachability. You also have a couple of smaller variants of this problem. So in full generality, the problem is denoted by dk.dk. It's case 3 down here, where we have these graphs and we have these different interleavings of the symbols of the two languages. Now, if you take one of the two languages and think that you only have one pair of parentheses, then you're essentially replacing your stack with a counter. So instead of looking at what are the contents of your stack, you just count how many parentheses you have seen so far. So whenever you open one, you do a +1. Whenever you close one, you do a -1. And this gives rise to the simpler, seemingly at least simpler problem of DK-D1 Dyck reachability. And well, when you have counters on both languages, you're basically in the D1 case, which is illustrated by this simple graph up here. So hopefully the setting is clear now. What do we know about this problem? Well, we know a few things, but not that many. So first of all, the D1 case, well, this is also known as a two-dimensional vector addition system with states, and reachability there is in NL and therefore also in P time. And this even holds for the non-bidirected case. So there was a nice paper last year which showed that actually you can solve the bidirected case in n to the 7th time. And it also showed that if you go to the fully general case of decay reachability, well, the non-bidirected case, we know it's undecidable. The bidirected one, we know now it is at least NP-hard thanks to this paper from last year. So, right, so this paper now that I'm presenting is essentially extending existing results and building a fairly rich landscape around this problem. So in one slide, I'll just give you the results that we get. We consider all variants. First, we look at this D1 case, which is the simplest one. And we, in fact, establish a bound that is essentially cubic. Alpha n here is the inverse Ackermann function. So this is a kind of significant improvement from the n to the 7 down to n cubed. We go to the DK-D1 case, and we show that the problem is, in fact, decidable. So, you can consider richer formulations. This is a more expressive formalism than the D1 case. The problem remains decidable. So you can take and use this. It is also theoretically interesting because without bidirectness, well, the problem is also known as push-down vector addition systems in one dimension where the decidability of reachability is currently open. Right. Now, of course, if you want to use these in practice, simple decidability does not suffice. You would like to have an efficient algorithm. So in order to do that, we consider a kind of a restricted version of the DK-D1 problem, where basically we look at what happens when we only consider paths where the counter, so whatever effect you have on the second language, stays linearly bounded. So you don't consider witnesses where the counter can grow very large. Right. So here we saw that the problem actually can be solved very efficiently, essentially in quadratic time. And we also saw that this is fairly tight. So the problem is hard for orthogonal vectors, which is a way of saying that it is unlikely to have any polynomial improvement beyond this quadratic bound. So essentially, this algorithm is optimal. Right. And now we go to the fully general case, the most interesting of all. Unfortunately, here the problem remains undecidable. So this tells you that bidirectedness does not add any easiness to the problem. It remains Turing complete. Right. So this is essentially the main results that you can find in the paper. Now I'll just use the rest of my time to just give you a brief insights behind these two results, the two extreme, right? The better one in the simplest case and the full undecidability, which is what we would like to solve. So for the D1 case, here, recall that we are essentially dealing with counters. We just have a graph that manipulates two counters. And we're in the bidirected case, so we can traverse edges forwards and backwards with complementary effects. And well, the theorem that we established here, as mentioned in the earlier table, is that you can solve this problem in essentially cubic time. N is the number of nodes in the graph, and alpha is this inverse Ackermann function, which for all practical reasons, it's at most 5 or something. Right, so the key insight behind this theorem is kind of a structural lemma here that tells you that, well, without loss of generality, whenever you're looking at path witnesses between nodes, you can assume that the counters stay quadratically bounded. So if you are to have a witness path that witnesses the reachability of one node from another, you may as well assume that the counters along this path never grow beyond the quadratic bound. So this is the key observation. And now how can you use this to derive an algorithm? Well, again, here is the observation that bidirectedness allows you to conclude boundedness on the counters. And well, okay, before I tell you how to use this, I'll just give you the brief intuition about why this holds. So if you consider that we just have one counter instead of two, in general, without bidirectedness, the counter might become quadratically large. But in a bidirected graph, you can show that the graph will never become more than linearly large. And the idea is that as you have a path from left to right, this path P, that is a witness of reachability, and here the y-axis looks at how large the counter becomes. Well, the idea is that, well, if your counter at any point reaches the value of 3n, then on its way from 2n up to 3n, it must have traversed a positive cycle h here. Right? It must have increased n times, and well, because you only have n nodes, and any simple path would have n-1 edges, so you must have traversed n edges. This tells you that it must have a positive cycle. And well, since this is a witness path, closer to the end, the counter must become smaller and smaller and eventually zero, which means that you also have to traverse a negative cycle on the way down from 3n down to 2n, right? This is a cycle C. So because of bidirectedness, you can actually flip the order of these two cycles. So whenever you traverse the path and you arrive at y down here, instead of traversing h, you might as well skip it, continue down all your way down to x, traverse the negative cycle, then go back to x, go all the way back, skip h again, and now find yourself again in y, while you have kind of proactively traversed the negative cycle before the positive one. So in effect, the big counter value that you reached here of 3n will have decreased by whatever the amount of the negative cycle is. So this kind of rearrangement is possible because you have bidirectedness, and this allows you to conclude that if you just have one counter, well, you might as well assume that it stays linearly bounded. And now when you go to two counters, which is the case that we're starting here, this kind of reasoning is more involved, but still of similar flavor, and allows you to conclude a quadratic bound instead of a linear one. Right? Hopefully that's kind of clear. Now, well, you have this quadratic bound. What do you do with it? Well, the idea is fairly simple. You start with this bidirected graph with two languages on the left, and you're gonna create n squared copies of it.